Hello students, let's begin with something familiar. When you open a bottle of antiseptic like Dettol, that sharp smell comes from chlorinated aromatic compounds. But have you ever wondered how these halogens are actually prepared in the lab? An LT, break time is equal to 0.5 SNGT. Unlike haloalkanes, we cannot simply replace an O group because phenols have a very strong carbon-oxygen bond. Instead, we rely on clever methods like electrophilic substitution and diazonium chemistry. An LT, break time is equal to 0.5 SNGT. These techniques, with the right catalysts or conditions, allow us to place halogen atoms directly onto the benzene ring. Today, we will explore these fascinating methods step by step.
Let's start with the most direct approach. Benzene can react with chlorine or bromine in the presence of a Lewis acid catalyst such as iron or iron 3 chloride. The reaction follows an electrophilic substitution mechanism. For example, benzene plus chlorine in the presence of FeCl3 gives chlorobenzene and hydrogen chloride. Similarly, benzene plus bromine with Phe3 produces bromo-benzene and hydrogen bromide. The products formed are usually ortho and para isomers, which can be separated because of their different melting points. However, this method does not work well for fluorine because it is too reactive, and iodination is reversible unless we add an oxidizing agent like nitric acid or periodic acid. This makes electrophilic substitution best suited for chloro and bromo-benzenes. Let's look at a very important transformation in aromatic chemistry: the Sandmeyer reaction. When a primary aromatic amine is treated with sodium nitrite and hydrochloric acid at a low temperature of 0 to 5 degrees Celsius, it forms a diazonium salt. The reaction is RnH2 plus NaNO2 plus HCl at 0 to 5 degrees Celsius gives Rn 2 plus Cl minus plus NaCl and water. These diazonium salts are very useful intermediates. When they are treated with cuprous chloride or cuprous bromide, the diazonium group is replaced by chlorine or bromine. The general reaction is Arn 2 plus Cl minus in the presence of CuCl gives Rcal plus nitrogen gas, or Rn 2 plus Kl minus in the presence of Cubor gives Arbor plus nitrogen gas. This is called the Sandmeyer reaction. It is widely used in aromatic substitution to selectively introduce chlorine or bromine into the benzene ring. And remember, nitrogen gas is released, making the reaction irreversible. Now let's see how we can prepare iodoarenes. Interestingly, iodination of benzene through electrophilic substitution is not efficient because the reaction reverses easily. But diazonium chemistry gives us a simple solution. Benzene diazonium chloride, when treated with potassium iodide, directly forms iodobenzene, releasing potassium chloride and nitrogen gas. This reaction doesn't require any copper catalyst. Just shaking the diazonium salt with potassium iodide is enough. That's why diazonium salts are considered the most practical route to aromatic iodides. At this point, let's compare the methods. Electrophilic substitution is quick and works for chlorine and bromine, but it has limitations for fluorine and iodine. The Sandmeyer reaction is versatile, allowing controlled introduction of chlorine or bromine through diazonium salts. Direct substitution with potassium iodide is best for iodoarenes. SAT. Each method requires different reagents and conditions, so the choice depends on which halogen you want and the purity required. Industrially, electrophilic substitution is common for bulk chloro and bromo-benzenes, while in the lab, diazonium chemistry is preferred for precision. Let's apply what we've learned in an example. Suppose we want to convert aniline into chlorobenzene. Step 1 is diazotisation. Treat aniline with sodium nitrite and hydrochloric acid at 0 to 5 degrees Celsius, and we obtain benzene diazonium chloride. Step 2. React this diazonium salt with cuprous chloride and nitrogen gas escapes, leaving us with chlorobenzene. So overall, C6H5NH2 converts to C6H5N2 plus Cl, which then gives C6H5Kl. This example shows how diazonium salts serve as a versatile platform for substitution, with the release of nitrogen gas driving the reaction to completion. So, let's wrap up. We saw that haloarenes can't be prepared the same way as haloalkanes because phenols resist substitution. Instead, 3 key methods are used. First, electrophilic substitution with chlorine or bromine in the presence of Lewis acids like FeCN3 or FeBr3. Second, the Sandmeyer reaction, where diazonium salts replace the amino group with halogens like chlorine or bromine. And third, direct substitution of diazonium salts with potassium iodide to form iodoarenes. Each route has its own strengths, and the choice depends on the target halogen and desired control. This is the beauty of organic synthesis. The same benzene ring can be transformed into a variety of haloarenes using different strategies. I hope this session gave you clarity on how chemists cleverly use these reactions to design important aromatic compounds. See you in the next class with more amazing insights from the world of organic chemistry.